Right, so let's expand on our concept of boiling and phase transitions in general, and let's talk about evaporation and boiling. So for example, if you have a cup of water, right, there's my water, and you leave it out on the counter or whatever for several days, or longer or shorter or whatever. What you're going to notice is that eventually there's going to be less water, right? Nothing too groundbreaking there. Some of it has evaporated away. And so what we have here is a phase transition, a liquid to a gas phase transition, but we have no boiling. Right, but we just said, hey, the phase transition from a liquid to gas is boiling. So kind of what's going on here, and what we have to do is adjust our mental model of what's going on in these compounds. So when we think about boiling and whatnot, we think about what temperature that occurs. And remember that temperature is the average kinetic energy, right? So it's a measure of average kinetic energy, right? That term here, average, is very important because when you have an average of something, you're going to have some that have more and some that have less. So for example, if we drew this plot right here, where over here we had fraction of molecules, which is basically just how many molecules are existing in that state. And then here we had kinetic energy. The distribution would look something like this. Let me draw a little bit better. Right, and then your temperature, your average would be somewhere there in the middle. But what you can see is that there's some that have a much higher level of kinetic energy. And then we can arbitrarily just draw a line somewhere down here, and we'll say that this is the energy required to go from a liquid to a gas. And so we can see that even though our average is below this energy required, some molecules do have enough energy. So some molecules go from liquid to gas without boiling. Right, and that makes sense, based on our everyday observations, things evaporate. And then let's go ahead and just take a look at the molecular view of this. So we have our cup of water again. This time I'm going to make this a dark blue. And we've got liquid water right here. And so anytime you have a liquid, it will experience some level of vaporization, right? Some level of going from a liquid to a gas without boiling. And so some of these molecules of liquid are going to be turned into a gas that I'll indicate right here, and vice versa, right? These molecules are going to be jumping back and forth from the liquid and gas phases. And anytime we have a gas, that gas is going to exert pressure. And this is what's known as vapor pressure. Vapor pressure is the pressure of a gas above a liquid, right? The pressure of its vapor. And we can think about where overall it's exerting that pressure. Since it's in a cup, right? It's exerting that pressure in an upward motion. But if we think about what's going on in our everyday life, in our everyday circumstances, we don't just live in a vacuum. We live in an air, which also is a gas, and then exerts its pressure, right? So we've got an atmosphere that's pushing down on it. And so we can think of these two forces as fighting one another. The vapor pressure of the water is pushing up, the atmosphere is pushing it down. And so we kind of have a battle here. And most of the time, right, the atmosphere is going to win. We're not going to see anything really going on there. But when we reach boiling point, right, when we get to boiling, what that means is when the vapor pressure is equal to or greater than the atmospheric pressure. Right, so the boiling of a compound isn't actually a direct consequence of its temperature, but really it's about this battle between the two pressures. And we get boiling when the vapor pressure beats out the atmospheric pressure. And so what does temperature have to do with it? Well, temperature controls how much vapor pressure we have. So as we heat, we make more gas molecules and increase vapor pressure. And so when we say that water boils at 100 degrees Celsius, what we mean is at 100 degrees Celsius, the vapor pressure is greater than or equal to the atmospheric pressure. But that's only under normal circumstances. So we call that the normal boiling point. And that's the temperature that you're going to boil at 1 atmosphere, at approximately sea level. But not everything is at sea level, right? If we have different atmospheric pressure or different altitude, we're going to have a different boiling point. And so as we increase in altitude, we actually decrease in atmospheric pressure. And thus we lower the boiling point. So say you're on top of, a super high mountain, Mount Everest. That water is going to boil at less than 100 degrees Celsius. And that's because you have less atmospheric pressure. And so it's easier for the vapor pressure to beat it out. And this has like a pretty cool common day application, at least if you live in the high altitudes. And that comes when cooking, right? So if you've ever gone up to the mountains and you've cooked, or maybe you know somebody that lives really high up, they oftentimes have to cook slightly differently, right? So in this case, this is just something I pulled from the internet, right? Some kind of instant pot cooking thing, right? And you can say that it says increase cooking time by 5% for every 1,000 feet over 2,000 feet elevation, right? And so what that's telling us, as we go up in elevation, our water boils at lower temperatures. And since we need to cook our food, right, that's based on the temperature of the water, you're going to have to cook it for longer because you're cooking at a lower temperature. So need to cook longer because water boils at lower T's at higher altitudes.